Hey, this is Xiuming Zhang from MIT CSAIL. Today, I'm excited to present neural light transport for relighting and view synthesis. Relighting has a lot of applications, for instance in VR and AR, or post-capture photo enhancement. However, relighting is hard. It's hard in two aspects, what I call the local aspect and the non-local aspect. Locally, the geometry has to be good, because otherwise bumpy normals would lead to noisy rendering. Besides geometry, the reflectance is often spatially varying, so we need different BRDFs at different points in the scene. For instance, the blue and yellow dots shown here, they are spatially very close, but the hot dog bun reflectance is very different from the ketchup reflectance. On the non-local aspect, shadows are hard to model as a global light transport effect. For instance, the pixel pointed by the blue arrow there is yin shadow because far away hot dog bun is casting shadows there. And of course, we also need to consider global illumination. In this example, the Lambertian green wall is casting green tint onto the white dragon. In this work, we present neural light transport for relighting and view synthesis, or NLP for short. It's a unified framework for directional or image-based relighting, view synthesis, or both tasks at the same time. Let's frame the problem of figuring out the radiance at location x as that of interpolating a light transport function, where x is the location on the surface, 2 degrees of freedom, omega I, the incoming light direction, another 2 degrees of freedom, and omega O, the viewing direction, the final 2 degrees of freedom. So this is a 6D function that returns RGB colors. If we have access to F and query it at novel omega O, we can synthesize novel views of the scene. Neural volumes is one paper doing that, and it doesn't change lighting. If we query F at novel omega I, we can relight the scene. Light stage super resolution tackles this problem, and the viewpoint is fixed. If we want to change both views and lighting, we can first synthesize one novel view of the scene and then relight that view. Deep view synthesis is one such approach that adopts this two-step procedure. Dual photography demonstrates how to synthesize the scene's appearance from the projector's view, pointing out that cameras and lights are really no different. Partially inspired by it, we treat cameras and lights equally in the work, and build a unified framework for view synthesis and relighting. So we captured our data using a light stage with about 330 lights and 55 cameras. The lights are turned on one light at a time, or OLAT, with the person sitting still in the light stage. So these captured images are essentially slices or samples of the 6D light transport function f. Now, if we interpolate between the physical lights, we are relighting the scene with non-existent virtual lights. Or if between physical cameras, we are synthesizing novel views of the scene from non-existent virtual cameras. Doing both at the same time allows us to super resolve the light stage in terms of both cameras and lights. So the rendering equation responsible for what the physical cameras see is this, where Fs is the 6D light transport function that we have already discussed, and Li is the incoming light direction masked by light visibility, and the rest is just the cosine term. From the light stage data, we can compute the diffuse render, assuming Lambertian. It is the product of albedo rho, incoming light Li, and the cosine term. How do we compute albedo for a real capture? We'll come back to that later. Note that the incoming light Li here has been masked by light visibility, and this essentially adds hard shadows to our diffuse space. To compute the light visibility, we simply cast rays from a light to the geometry proxy, and the geometry is given by the light series active scanning, and it may be noisy. The NLT network aims to bridge the gap between the full render and the Lambertian base by predicting non-diffuse residuals. These non-diffuse residuals include specularities and global illumination, and many more. So the benefits of predicting residuals rather than directly predicting the final RGB color is that the diffuse render already provides base colors and physically correct hard shadows, so that the network can focus on learning more complicated, higher order light transport effects, such as specularities and global illumination. We embed the function into the UV space, computed from the geometry proxy we previously mentioned. Using the UV space is key to handling viewpoint changes. We provide light and viewing directions in the form of cosine maps, where we dot product the directions with the surface normals. Again, the geometry proxy is from the light stage's active scanning and can be very noisy. We then ask the network to predict the RGB values for each texel. The predicted texture map gets then resampled back to the camera's perspective and compared against the ground truth captured image. We also feed in a physically correct diffuse-based rendering, so that the network does not need to learn the albedo and hard shadows from scratch. To compute the diffuse space, we first add up all of the OLED images to simulate turning all of the lights on the light stage, which gives us approximated albedo. We then modulate the full lit image with the light cosines and mask it with both view and light visibilities. The visibilities are computed using the geometry proxy, and the light visibility essentially adds hard shadows to our diffuse-based rendering. There is also a skip link from the diffuse space to the network's prediction to explicitly tell the network to focus on learning higher order light transport effects, such as specularities and global illumination. Finally, we have an observation path to additionally encode what the non-diffuse residuals look like for neighboring observed lights and views. Such observation features get averaged and concatenated back to the query path for it to decode the query view residuals. Because the observation feature maps get averaged, the network can handle an arbitrary number of observations. Now let's look at some results, where we relight the person with a directional light, and the viewpoint remains unchanged in this case. So these are the light directions and the corresponding images used for training. Notice that here the viewpoint never changes. Our prediction adds specularities and global illuminations to the diffuse space, as indicated by the blue and yellow arrows respectively. It also compensates for geometric inaccuracy visible in the diffuse space, indicated by the green arrow. And this is why I said we need only a geometry proxy rather than the actual perfect geometry. It is also more than just copying from the nearest neighbor, as seen from different shadow boundaries indicated by the yellow arrows here. Here are more directional relighting results. Notice the light-dependent effects, such as facial specularities and the specularities on the lady's jacket. We also have cast shadows. By linearly combining the directional relighting results, we can relight the person according to any arbitrary light probe. Here are some results for relighting the person with a light probe. We can also synthesize novel views of the scene with view-dependent effects. Here are the camera locations and the corresponding images used for training. Notice that here the lighting doesn't change. Now we are rendering the person with an arbitrary smooth camera path. At scene, it doesn't work to just render the captured geometry using a Lambertian BRDF or just copy from the nearest neighbor. Here are more view synthesis results. Notice the view-dependent effects, such as facial specularities. Some more results on view synthesis. We compare our method with NERF, a state-of-the-art view synthesis model. It has the benefit of not requiring any geometry, but it doesn't support relighting. Next, I'm going to flip back and forth between our results and NERF's results. We also compare our method with deferred neural rendering in view synthesis. Flipping back and forth. We show how our model simultaneously relights and synthesizes novel views of the scene. Here are the cameras and lights and their corresponding images used for training. These data have both viewpoint and lighting variations. At test time, the light first follows the camera exactly in doing a 360 and then diverges into a spiral path. Here are some more results on simultaneous relighting and view synthesis. Finally, we extend NERF to support simultaneous relighting and view synthesis by conditioning its output radiance also on the light direction, in addition to the original viewing direction. We trained this extension with the same data that we used to train NLT and compare this extension against NLT. Because unlike NLT, NERF plus light lacks physical modeling of shadows. It's having a hard time synthesizing the hard shadows in this case, as indicated by the red arrow. Next, I'll flip back and forth between NERF plus light and NLT. So to summarize, we have three contributions. Firstly, we've presented a unified framework for simultaneous view synthesis and relighting by embedding networks into the texture atlas. Second, this is a residual learning scheme on top of a physically correct diffuse space, which together allow the network to easily learn non-diffuse, higher-order light transport effects. Third, this is a semi-parametric neural method for interpolating the 6D light transport function. Please check out the project page for the paper, technical video, and code. Thanks for watching.